Welcome back, chemists. In this video, we are going to continue our discussion of valence bond theory by talking about something called hybridization. After today, you should be able to identify the hybridization of an atom in a molecule and predict the overlapping orbitals in a molecule. Atomic orbitals, the s, p, d, f, etc., can blend together to form new orbitals when atoms are covalently bonded. These hybrid orbitals point in directions different from the original orbitals. The number of hybrid orbitals formed is equal to the number of orbitals used to form the hybrids. For example, we all know that the carbon atom has the electron configuration of 2s and then 2p with 2 electrons in it. And so my question to you is, how can carbon make 4 bonds when it only has 2 empty p orbitals? And so this is where hybridization becomes a very effective tool to help us understand how this must happen. So that must mean that an electron experiences what we call electron promotion and is pushed into that 2p orbital. So the 1 extra electron from the 2s there is going to be promoted into the 2p. And now what happens is that these orbitals must blend together to form new orbitals, because we know that the energy of these orbitals is identical. And so what happens is the 1 from the 2s and then the 3 orbitals from the 2p are now going to blend together and form 4 sp3 hybrid orbitals, all equivalent in energy. The other thing that's important to note is if you think about the shape of the p orbitals, remember how they're all oriented at 90-degree angles to each other in 3-dimensional space? Well, this is important because with something like methane, we know that experimentally the bond angle in methane is 109.5. So how can we explain this bond angle? And hybridization also helps us to do just that. And so basically we say that we can blend those atomic orbitals to make these new things called hybrid orbitals, all of equal energy. So instead of having 2 electrons in the 2s and 2 electrons in the 2p, now we have 4 electrons in this new hybrid orbital called sp3. Let's talk about the hybridization of NH3. So there's NH3, and the electron configuration orbital notation for the nitrogen atom is going to be something that looks like that. And notice again, we don't really need any electron promotion here because we see that we have 3 open spaces for the hydrogens to interact with those electrons. But instead, again, we know that these orbitals are equal in energy, so therefore we have to blend them together. And now again, we take the 1 from the 2s and then the 3 orbitals from the 2p and blend together to get the sp3 hybrid orbitals. And from this configuration, we can very clearly see that where the arrows are pointing, that is the configuration for the unshared pair of electrons, and then the 3 unpaired electrons where the hydrogens can slide in and share those electrons. With something like BF3, remember this is an exception. I did not include the unshared pairs on the fluorines because we're really focusing on the hybridization of the central atom. So for boron there, the orbital notation for boron is going to be 2s2 and 2p1. But again, as you can very clearly see, there are no spaces for all the fluorines to combine, right, and attract a second electron. So what we're seeing is going to happen, the electron in the 2s is going to experience electron promotion and go to the open 2p orbital. And notice you have an empty 2p orbital. There's no electrons in there. So what we call this is an sp2 hybridized set of orbitals. So the 3 orbitals that come together, the 2s and then the 2 of the 2p's, come together to form 3 sp2 hybrid orbitals that are equal in energy. So now let's look at the hybridization of BeCl2. Remember, BeCl2 is an exception as well. Beryllium satisfied with 4 electrons around it, and I did omit the lone pairs around each chlorine atom because we're focused on the hybridization of the beryllium, or the central atom. So this is the orbital notation for beryllium. Notice there's 2 electrons in the 2s, and so again, there's no space for another chlorine to combine or attract that electron. So what we do is we take the electron in the 2s, promote it to a 2p, and we take the 1 orbital from the 2s and the 1 orbital from the 2p and make a combined hybrid orbital of sp. And notice we have 2 unhybridized or empty 2p orbitals. So now let's talk about how to tell what the hybridization is going to be. So if you weren't following what I was trying to make sense of earlier with looking at the different hybridization, there's a really easy way to tell. It's really based on the number of electron domains. So the geometry expression helps us to identify the hybridization on the central atom. So for example, if you have your terminal atoms and your electron pairs equal to 4, that is going to be called sp3 hybridized. There are 4 electron domains. If you have terminal atoms plus an electron domain equals 3, then this is going to be sp2 hybridized because there are 3 electron domains. If these 2 things equal 2, then it's considered sp hybridized. And then if you've got an x plus an e equal to 5, then that's going to be an sp3 dehybridized. So that would be 5 electron domains. And then finally, for 6, it would be sp3 d2 hybridized for 6 electron domains. So all you literally have to do is just count the number of electron domains, and that will help you figure out what the hybridization is. So here's the procedure for determining hybridization. First thing you have to do is draw the correct Lewis structure of the molecule. Then you predict the overall arrangement of the electron pairs, the molecular and electron pair geometries, and then match the areas of electron density with the hybridization. So again, if it has 3 areas, it's going to be sp2 hybridized. So you may say, what happens when you have double and triple bonds? What happens there in terms of our hybridization? Well, the good news is that the same rules apply. So for example, in ethene here, we've got 3 electron domains around each carbon. So automatically we know that it's going to be sp2 hybridized. But we know that that electron still needs to experience electron promotion so that it can go into the 2p. Now, what happens is we form those hybrid orbitals out of the 3 orbitals that we need for each hydrogen to overlap. But then there's a remaining electron in an unhybridized 2p orbital. So there's an unhybridized 2p orbital on each carbon, and this is what is used for the pi bond in that double bond. So if you have a double bond, there's always going to be one unhybridized p orbital so that it can make that pi bond. So you might want to make a note of this in your notes. When you have a pi bond, there must be unhybridized p orbitals. If this were a triple bond, then you would have 2 unhybridized p orbitals. So again, I'm going to direct you into making sure that you view this video, because this video, it was what I showed you earlier with focusing on overlap above and below the plane for pi bonding and then head-to-head for sigma bonding, but now this talks about it in terms of hybridization. So I'm going to ask you to rewatch this, and I will put a link in the description as well so you can view it. So that is the end of our discussion of hybridization. I'm going to ask you to please complete the exit ticket, then begin worksheet 2H. Thank you so much for watching.